ways which previously seemed impossible. My name is Matthew Purcell, and I'm a Senior Technical Trainer at AWS, specialising in artificial intelligence and machine learning. I am so excited to be guiding you on this journey today. Before we get started, it's worthwhile that we stop, take a breath, and look at where we are right now in technology. Over the past decade, there's been significant innovation in technology, particularly in the field of artificial intelligence. And we find ourselves at a crossroads, where the lines between what is created by humans and what is created by machines is increasingly blurred. Questions are being asked. How will this affect human society? What are the applications for business beyond novelty value? What guardrails are being placed around responsible use of these technologies? These are all important overarching questions, which we're going to aim to address today during our journey into generative AI. We're going to start by looking more broadly at what is artificial intelligence and machine learning, before diving into the different types of machine learning that ultimately leads us to the focus of our session today, generative AI. After looking at how generative AI works, we'll consider the applications of this technology together with practical use cases. We'll finish off our session considering the challenges of artificial intelligence in society, particularly surrounding the responsible use and implications of generative AI. I also want to take a moment to level set and tell you what this session is and is not. This session is all about demystifying and empowering you with an understanding of how generative AI works in a no-nonsense, understandable way. And this will be the focus of our time together. We'll also cover some of the practical uses of generative AI, along with responsible use considerations. This session is not a deep dive into how to deploy generative AI on AWS. There are already great resources available, such as blog posts and online workshops covering that in depth. Instead, in this session, we want to equip you with the foundational knowledge, so if you do decide to deploy generative AI, you have an understanding of how it's actually working. Let's start off by looking at how generative AI fits into the broader field of artificial intelligence. Artificial intelligence involves simulating human intelligence and decision-making by building algorithms, essentially computer programs, to take and process information which inform future decisions. A very simple AI could be developed using a traditional programming approach, where there are a series of manually defined rules specified by the computer programmer, each returning a result depending on which rule or rules have been met. However, there are issues with this approach. The first problem is scalability. In many cases, it's difficult to anticipate and identify all the rules and code them into the application. For example, how did we determine the optimal air conditioning heating threshold is 20 degrees? The second problem is adaptability. When there's new data and situations, the old rules simply might not work. You would need to hand design new rules or modify existing ones. For example, what happens if a new person moves into that space? They might have a different temperature preference. The third problem is that hand-designed rules assume we have a complete understanding of all situations, which we know is not always possible. So we might miss important rules because, well, we didn't even think of them. For example, what if a window or door is open? We might want to do something different, like turn the system off entirely. So wouldn't it be great if we could instead provide the computer with some sample data, also telling it the correct result for each piece of data, and it could automatically derive the rules to reach those results? Well, we can, and we call this approach machine learning, as, well, the machine is learning. Based on its learning, the computer builds and outputs a machine learning model. This model is essentially a computer program which can be used to find patterns or make predictions for new and unseen data. We could provide the model with data it hasn't seen before and we don't know the intended result, and it could use the rules it's automatically derived to provide us with a predicted result for that new unseen data. Now there's three main types of machine learning: supervised learning, unsupervised learning, and reinforcement learning. In supervised learning, every individual piece of training data, known as a training example, has a corresponding label associated with it, which essentially tells the machine learning algorithm what the training example is. As a result, the algorithm can then learn from this data to predict labels for unseen data in the future. In this example you see here, the algorithm is being trained to identify flowers, which we call the target. So it will be given training data with images of flowers along with the kind of flower each image contains, and we call that description the label. The algorithm then uses this training data to learn and identify flowers in unseen images it may be provided in the future. In unsupervised learning, there are no labels for the training data. The machine learning algorithm tries to learn the underlying patterns or distributions that govern that data. In this example, the training data given to the machine learning algorithm does not contain labels to predict, but instead must identify patterns in the data itself. This can often be of benefit since it allows you to use massive data sets where labeled data may not be readily available. Finally, reinforcement learning. Now this is very different to supervised and unsupervised learning. In reinforcement learning, the algorithm learns from experience and experimentation, essentially trial and error. In this example, we're training a robotic arm in a fulfillment center to pick up boxes on a production line and place them onto mobile platforms for transport. During training, if the robot arm successfully places the boxes onto the transport platforms, then a positive reward is issued. However, if the robot arm gets it wrong, perhaps not grasping the box or it places it incorrectly, then no reward or a negative reward is issued. So over time, through a cycle of exploration and exploitation, the robot learns the correct actions to take in order to maximize rewards. So that completes our three types of machine learning. And now that we have an understanding of what is machine learning, you might be wondering, well, how does machine learning actually learn? Going back to our diagram, we're looking at this bit of the process here. How we teach an algorithm to learn by itself, which then results in a model being output, allowing us to make predictions on unseen data in the future. There are a whole range of different machine learning algorithms, each designed for particular use cases and may use supervised, unsupervised, or reinforcement approaches, or even a combination. Let's take a very simple example. Who remembers linear regression from doing maths at school? All I can remember is drawing a line of best fit and knowing that I'd probably never use that knowledge. Well, the time has come to apply that towards machine learning. There's a simple machine learning algorithm called linear learner, which is typically used for supervised learning tasks. Based on the training data, this algorithm attempts to find the linear line of best fit through the data. As we've mentioned, this trained algorithm is called a machine learning model, a computer program which has been trained to identify patterns in data, so when it's presented with new unseen data, it can make a prediction. In the example of our linear learner, the model would contain the linear relationship, allowing future predictions to be made following that relationship. Now, this is a simple example with one feature, being hours studied, predicting the target variable, the exam score. You could easily do this on paper, but what happens if you need to do this to represent a relationship between 3 features, maybe 4, maybe 100? This would be impossible to do manually on paper, but linear learner can do it for you. This algorithm performs best when the relationship between input and output is roughly linear. And there are other algorithms which can be used for nonlinear relationships, clustering of data, anomaly detection, text classification, and so forth. This kind of machine learning algorithm is known as a traditional algorithm. These are some of the most common algorithms used for business use cases. But let's say you're presented with a machine learning problem that's very complex, such as image recognition or natural language processing. Traditional machine learning algorithms might not be suitable at addressing these kinds of problems with complex, multidimensional relationships between features. This is where deep learning comes into play. Deep learning is a subset of machine learning and can be used as an alternative to traditional machine learning algorithms. When using traditional machine learning algorithms, you need to manually select the features of the dataset which you think have the highest predictive power. Using our previous example, the mark you would receive based on hours of study is fairly simple as it uses a single feature, hours of study. However, most problems involve using multiple features. For example, when training a model to predict house prices, the features might include the number of bedrooms, location, and square footage of the house. The data may also need to be engineered, meaning modified or transformed to be more meaningful, such as normalizing the number of bedrooms and square footage to be on similar scales, so that one feature does not dominate the other purely based on the range of their numerical values. In contrast, deep learning is able to automatically learn and extract features from the training data and understand complex relationships and patterns to make accurate predictions. This is useful when features in the dataset have relationships too complex to allow the features to be manually selected and engineered. Now you might be wondering, wow, this whole deep learning thing sounds pretty good. Like, I don't have to do manual feature selection and engineering, so why don't we just use it all the time instead of traditional machine learning algorithms? Well, it really comes down to the data requirements along with time and cost. Deep learning models often require a large amount of labeled data along with significant amounts of compute power and training time. On the other hand, traditional machine learning algorithms can often achieve good results with smaller datasets and less training time. However, the reality is that for more complex problems, deep learning is often the only way to go. Let's now look at how deep learning works. The foundation of deep learning are artificial neural networks. This is a computational model inspired by the structure and biological connections and neural networks in the human brain. To demonstrate how an artificial neural network works, let's use a very common example. Given a handwritten digit in the range of 0 to 9, you want to identify the digit. To do this, we're going to train a deep learning model using an artificial neural network by providing it with images of handwritten digits along with labels identifying what digit each image is representing. Now, the keen-eyed amongst you might notice we're using a supervised learning approach here to train our deep learning model. Note that we just have a small representative selection of digits here. In reality, we'll be training with thousands upon thousands of examples. In fact, the dataset we're using here, called the MNIST dataset, has 60,000 training samples. So getting back to it, an artificial neural network is based around things called neurons, similar to the neurons in the human brain. Each neuron performs some kind of transformation or computation on its input. These neurons are organized into layers, where all the neurons in a layer perform the same computation on their input. The first layer in the artificial neural network is called the input layer. This layer accepts the input into the neural network and feeds it into subsequent layers of the network. More about that a bit later. In our example, the input is a 28 by 28 pixel image. Usually the input layer has a neuron for each feature or dimension of the input. So in this example, each pixel in the image will be sent to an individual neuron in the input layer. So there'll be 784 neurons in the input layer in this case for a 28 by 28 pixel image. Now, I know I said before that the neurons in each layer transform their input, but the input layer is an exception. In our case, these 784 neurons in the input layer don't really do much except be a conduit to transmit input values into the hidden layer portion of the network. Now, it's in these hidden layers that computations take place so that relationships from the input values can be learned. The reason we call these layers hidden is because they're internal to the network. We cannot see the input or output of the neurons in the hidden layers directly. Each neuron in the hidden layer performs one very specific, nuanced task. Every neuron is structured the same. They take a numerical input, perform a basic computation, and produce a numerical output. You might be wondering, how can it learn to do something pretty complex like image recognition? Do we need to program these neurons to perform a particular task? Well, you might be surprised to know, no, you don't. That's the magic of an artificial neural network. It will learn by itself. In fact, when we start out, the network has no knowledge of what it's supposed to do. It starts off completely generalized. Let's look at this in a bit more detail. Neurons in the network are linked together through connections. The particular architecture of the neural network dictates which neurons in one layer are connected to which neurons in another layer. Here, for example, we've chosen to implement what we call a fully connected or FC layer, where each neuron in the first hidden layer is connected to all the neurons in the preceding input layer. This gives each neuron in that hidden layer full visibility over the entire image to perform whatever processing or task needs to be done. Note that there are other architectures which do not use this approach. It greatly depends on the particular use case. But we'll use a fully connected layer now just to keep this example understandable. Now, as you can see, the diagram gets quite busy when we model all the connections. So for the purpose of this example, let's just focus on a single set of neuron connections. The exact same principles we discuss apply to the others. Each connection in the network has a numerical weight, which signifies the importance of that neuron's output towards achieving the grand goal of the network. In this case, correctly classifying an image of a handwritten digit. The numerical value output from the neuron is then multiplied by the weight of the connection, and that forms the numerical input into the next neuron. Let's say that the input into that first neuron was like a grayish pixel from the image, represented by the numerical color value 123. By the way, that's probably not actually the color value, I just made that up. Now, input neurons don't do anything to their input. They just pass it through. So the output of that neuron is going to be the same as the input, 123. That output is then multiplied by the weight, providing what we call a weighted output, in this case of 98.4, which then forms the input into the next neuron in the hidden layer. Now, it's common to have multiple inputs into a neuron, as is the case in this example with the neurons in the hidden layer. In this situation, all the weighted inputs into the neuron are added together to produce the weighted sum, reflecting the importance each input has in influencing the neuron. Now, you might now be wondering, how are all of these weights determined? Well, when the network is brand new and hasn't been trained, all the weights are typically initialized to completely random values. This ensures that the network does not have any preconceived biases or preferences for specific patterns or outcomes. During training, these weights are adjusted, which is how the network learns. We'll talk more about that shortly. This weighted sum is then input into the neuron's activation function. This is a function defined when you design the network and is the same for all neurons in a particular layer. This function maps the weighted sum output of a neuron into a null value, such as between 0 and 1. The activation function also contains a threshold which determines whether a neuron will be activated or fire, or remain inactive, not fire, based on that mapped or translated value. Now, this is the key to how different pathways can be taken through the neural network. We call this phenomenon non-linearity. In other words, the model and the artificial neural network can learn complex relationships and make non-linear decisions. In this example you see here, the neuron will be activated or fired as the value calculated from the activation function, 0.7, exceeds the threshold of 0.5. However, let's address a potential issue. Let's assume that as the network is learning, one neuron starts specializing in a specific task, like, let's say, identification of diagonal lines in the input image, such as those present in the number 4 or 7. Sometimes the diagonal line might be faint, or perhaps the model wasn't trained with a dataset with sufficient examples of diagonal lines. Whatever the case, this might result in that neuron not firing because the weighted sum doesn't exceed the activation threshold. As in our example here, perhaps because the input values are smaller due to the line being faint and the color values not being as strong. Fortunately, we do have a way to address this situation. Each neuron also has a bias. This allows for the adjustment of a neuron's output regardless of the input values. This is useful if, for example, we wanted to boost the likelihood of a neuron being activated, as it might not always be activated purely through the input values and weights. We also don't set the bias manually. This is done during network training. For example, if the network notices that it continually misclassifies digits with diagonal lines. So what we actually do to complete our story here is we take our weighted sum and add the bias before feeding the result into the activation function to see whether it exceeds the threshold for activation. If it does, then that output is fed as input into the next layer, which follows the same process. This results in the data propagating through activated pathways in the network and is known as forward propagation. In the example, the weighted sum output of only 2 neurons met their activation function's threshold, so only the output of those 2 neurons is propagated further into the network. This network currently only has one hidden layer, but it's possible to have multiple hidden layers. This builds upon the learnings from the first layer and enables the network to understand more complex features and relationships in the data. For example, here we're implementing a second hidden layer with neurons which can perhaps do things like feature composition to combine features such as corners and edges, which have been identified from neurons in the first hidden layer. Once again, remember that with fully connected layers, all the neurons between layers will be connected to each other. However, for simplicity of this diagram, we're only showing connections between select neurons. Alright, let's conclude our story now. The final layer in the network is known as the output layer. In our example, we have 1 neuron per category or class we are predicting. We have 10 classes, 1 for each number, so there'll be 10 output neurons, 0 through to 9. Just like the hidden layers, based on the input values and connection weights, a weighted sum with bias is calculated for each of the neurons in the output layer. This weighted sum with bias is then input into the activation function for that neuron, which produces an output meaningful to the particular use case. In our example of classifying a handwritten number into a class or category, being the number, we would use an activation function for the neurons in the output layer, which provides the probability of that handwritten number being a member of each class. The class with the highest probability is what the model would return as the number. In this example, the class with the highest probability is for the number 7. Now, the model has obviously gotten the prediction wrong, but that's okay, because the model has not been fully trained, so all the weights and biases were just randomly assigned. Remember we mentioned that before? Because we're in training, in addition to providing the input data, so for this network, image data, we also tell the model the correct class. It knows, as if you recall from before, we're using a supervised learning approach and provided the model with labels for the training data. This allows the model to know what the correct output should be, so it can calculate the loss, a way to quantify the magnitude of the mistake, or as we say in machine learning speak, the error. This information is then transmitted back through the network using a process called backpropagation, which updates both the weights and biases in the network. Now, we're not going to delve into the details of how that works here. That actually involves quite a bit of calculus, so we're simplifying things quite a bit here. However, what you need to understand is that this process of forward propagation and back propagation continues iteratively with different training data until the model has been trained so that it can make correct predictions most of the time. And this is the magic of an artificial neural network. When untrained, it's completely general with no knowledge of the task at hand. However, through iterative training and adjustments of the weights and biases, it can create optimal pathways through the network so that for that particular input data, in our case, images of hand-drawn digits, it will route to the correct output. In this case, prediction of that digit. And the basic building block of this magic are the neurons just performing simple numerical transformations on an input to produce an output. Just remember though, even though these individual neurons seem really simple, the real power of these networks is that they combine large numbers of these simple processing units into complex interconnected architectures, collectively allowing them to model complex patterns and make high-level decisions. In the previous section, we discussed the difference between traditional machine learning algorithms and deep learning algorithms, and now have an understanding of how artificial neural networks work as well. But what we're going to do now is we're going to look at the type of problems these machine learning approaches can be used to address. Most traditional artificial intelligence and machine learning applications, particularly in business, use discriminative or predictive AI. In this approach, the models are primarily concerned with predicting a value or providing a classification into a category or class based upon decision boundaries which have been learned. A very simple example of this approach is a machine learning algorithm which produces a decision tree, such as one to predict whether a house will be sold. We first specify the target, what we want to predict, being whether the house is sold or not. And we also specify the features, price, number of bedrooms, size, which we believe are influential over making the prediction. The decision tree algorithm learns the boundaries or rules which discriminate between different classes or cases in the data. In this example, sold or not sold, refining and optimizing the tree so that each split, the decision is made on a feature and value with the most discriminatory power. Once the tree is trained, predictions can be made on new unseen data by traversing the tree and following the decisions to reach a particular outcome. We often, although not necessarily exclusively, use traditional machine learning algorithms for these kinds of problems. This now brings us to the main topic of today's session that you've all been waiting for: generative AI. Unlike discriminative AI, where models just predict a value or classify input, generative AI enables the model to generate new data resembling the patterns observed in the training data. Additionally, models are trained to automatically learn the underlying patterns and relationships in the training dataset. Now, this might sound a little familiar from our previous section on artificial neural networks. And you're correct, generative AI uses artificial neural networks, but takes it one step further, allowing machines to create new content inspired by the data on which the model was trained. Let's take a look at two of the most common and well-known use cases for generative AI and how they work. Text generation has gained significant interest with the launch of tools such as ChatGPT, which allow users with no AI experience to interact with pre-trained generative AI models through a web interface. These use what's known as